Hello, let's discuss section 24.2, the chi-square test of homogeneity. In this section, we'll be working with a single categorical variable, just like in the previous section, but now there are several groups involved. We want to know, is the distribution the same among these different groups? That's a test of homogeneity. In fact, the term homogeneity means things are the same. The mechanics of this test are identical to the chi-square test for goodness of fit that we looked at last time. The two tests are different, however. With the goodness of fit test, we have a single categorical variable, and we compare the distribution with a theoretical model. Think back to the example from last time. We rolled a fair six-sided die 36 times, and we compared the results with the theoretical probability model, which says each outcome, 1 through 6, should occur with probability 1/6. With the homogeneity test, we have a single categorical variable, but there are several groups, and we want to compare the distribution among these different groups. The assumptions and conditions for the test of homogeneity are the same as for the chi-square test for goodness of fit. Let's look at an example. A random survey of autos parked in the student lot and the staff lot at a large university classified the brands by country of origin. Are there differences in the national origins of cars driven by students and staff? You can see the results of the random survey. Things are broken down by student and staff, and then origin of the car, American, European, or Asian. Now, it's important to think about how the data were collected. The researchers purposefully selected a sample of students and a sample of staff to query. They went to the student lot and randomly selected cars, and they went to the staff lot and randomly selected cars. So this is a question of homogeneity. We're going to examine the distribution of country of origin among the two groups to decide if those distributions are the same. Now in the next section, we'll look at a slightly different test called a test of independence. Had the researchers selected one large sample of individuals at the university and asked for auto origin and status, student or staff, they would have categorized each person with respect to two variables, and we'd be doing a test of independence to decide whether the two variables are independent. This is called a chi-square test of independence. So the distinction between these two tests is fairly subtle. Often you'll just be given a contingency table, and you'll have to decide which test to use. So in helping you decide, it's good to think about how the data were collected. We'd like to know if there are differences between students and staff in the national origin of cars, so we'll do a hypothesis test. For the null hypothesis, we hypothesize that the distribution does not change from group to group. In other words, the distribution of car origin is the same for students and staff. The alternative hypothesis is that the distribution of car origin is different for students and staff. Let's start by calculating expected counts. I've recreated the table here, and what you notice is overall 212 out of 359 of the individuals have an American car. So that amounts to 59.05%. If the distributions are homogeneous, as the null hypothesis asserts, then we'd expect that same percentage among students and among staff. So I'll take that percentage times the total number of students, 195, to get an expected count of 115.148. And I'll take that percentage times the total number of staff, 164, to get an expected count, 96.842. And I've written these in parentheses in blue, the expected counts. So we do a similar calculation. Overall, 45 out of the 359 individuals have a European car. So we'll take that percentage, roughly 12.53%, times the total number of students and times the total number of staff to get these expected counts. And finally, overall, 102 out of the 359 individuals have an Asian car. So we take that percentage, 28.41%, times the total number of students and the total number of staff to get these expected counts. Next, we calculate our test statistic chi-square, and this calculation is identical to the test for goodness of fit. We take our observed count minus the expected count, square it, and divide by the expected count, and then sum all of these. So for example, the observed count, 107, this was the number of students driving an American car, minus the expected count, 115.148, we square that and divide by the expected count. So we'll continue in this fashion and we end up with a chi-square value of 7.831. Now, determining the degrees of freedom is a little different here. What you do is you take the number of rows R in your contingency table and you subtract 1 and multiply by the number of columns C in the contingency table minus 1. So for us, we had 3 rows. So we take 3 minus 1 times, there were 2 columns, 2 minus 1, to get 2 degrees of freedom. To help see why the degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1, you could think about it this way. Once we've determined the entries in this first column, I mean the expected counts in this first column, we could take our total minus the expected count to fill in this expected count here. So in this case, we really just needed to fill in the first column, or similarly, once you've found the expected counts in the first 2 rows, you could subtract those from this total to get the expected count in this third row. Now it's time to calculate our p-value. This is the probability that chi-square is greater than 7.831. And you can use technology or a table to determine this. So I'll illustrate using the p-value calculator that we have a link to in our Canvas page. You enter the chi-square value, 7.831. Here we have 2 degrees of freedom, and I'll specify a significance level of 0.05. So we see that the p-value is 0.019931. And so the result is significant at an alpha level of 0.05. This p-value is less than 0.05. You can also use a table to determine the p-value. So you'd go to the row corresponding to your degrees of freedom. For us, it's 2. And then we need to find where our chi-square value is trapped. Our chi-square value is 7.831, so that's between 7.378 and 9.210. So we say here that our p-value is between 0.025 and 0.01, and that's what we saw using the calculator. With a p-value this low, we reject the null hypothesis at an alpha level of 0.05. The distribution of car origins differs between students and staff.